Welcome to Lecture 2. In this lecture, we continue our review of special relativity that we started in the first lecture. So last lecture, we started to review some of the basics of special relativity. In particular, we reviewed the index notation that will be very important for our calculations in general relativity. And we will continue some of this review in the present lecture. So to reiterate, last lecture we introduced the index notation that for ordinary three vectors would be just indicated by index I, and that is just meant to represent the individual components of the vector. So for instance, I going from 1 to 3 means we want to talk about the components x1, x2, x3 of some vector xi. Note that we can write products of vectors using this index notation by having the index appear twice. So for instance, ui vi will stand for the sum u1 v1 plus u2 v2 plus u3 v3. And we can also use index notation to represent more complicated objects, such as matrices. So for instance, an object that carries two indices, I and j, that where these two indices are different, will then denote a rank 2 matrix. In this case, I and j just represent the 9 entries of the matrix A, and these are just the components A11, A12, A13, and so on and so forth. So basically, the first index basically can be viewed as the row index. So 1, 2, 3 denotes row 1, row 2, and row 3. So note that row 1 always has a 1 for the first index here. Row 2 has always a 2 for the first index here. And row 3 has always a 3 for the first index. Whereas the second index would represent the column index. So this is column 1, this is column 2, and this is column 3. If we change the order of the matrices of a rank 2 matrix, then we basically perform an operation that's known as transposition. So if we again consider our matrix A here, that's given in this explicit form as a 2 by 2 matrix, we can consider the transpose of this matrix, which just means we want to exchange rows and columns. And then we have something that looks like this. So note that now, for instance, the entry A21 that first was appearing here appears up in the first row in the transpose of the matrix. If we look at the transpose of this matrix, we note that in the original index formulation, the transpose of the matrix just corresponds to changing rows and columns. And changing rows and columns, since the first index was the row index and the second index was the column index, if we want to do a transpose, we just exchange the order of the indices, such that what was before the column index becomes the row index, and now the row index becomes the column index. So long story short, the transpose of a matrix just means changing the transpose of a 2 by 2 matrix, of a rank 2 matrix, just corresponds to changing the order of the indices. We can also consider products of matrices in general, or matrices and vectors in particular. So if you want to calculate the dot product between a matrix A and a vector V, we can write this index notation by saying that we want to have a sum over the index j, our column index, with respect to the entries of the vector v. And if we write this out, we find that the individual, well, this object here is a vector because we have removed one of the indices. So the object that's left here has only one index left, that's the I. And that corresponds to now a vector that has the following entries. If you carry through the ordinary operation of the vector on the matrix, you'll get the same result as if you note that the first entry of this vector now has to be the sum over j of these two components. So in this case, this would be a11 v1 plus a12 v2 plus a13 v3. So note that the 1 here corresponds to the first entries of the index I, and the other entries are just summed over. So j is summed from 1 to 3, and that gives us the first entry in this new vector here. The second entry here is coming from I is 2, so the second row of the original matrix, and similarly for the third entry of this vector. So basically we can write products of matrices and vectors simply by having the same index appear twice in our formulation here. Note that the order of the product is in general important. So if the matrix A is not a symmetric matrix, then clearly the result of performing a vector product from the right is not the same as performing a vector product from the left. In index notation, the order of the product is uniquely specified by the index. In particular, it is the index that appears twice. That's the one that's corresponding to the product. So whatever that index is, that specifies which order you want to sort of take. Let's be a little bit more explicit about this. So consider an object bi that is formed by the matrix product of A with respect to V on the second index. Because the order of the product is uniquely specified by the index, we can simply change the order of the symbols. So Aij Vj is the same as Vj Aij because it is unimportant where the V is appearing. Which component of V is entering the product is uniquely specified by the index j, and the index j doesn't change. Similarly, we can consider a different object Ci, which you get by having a matrix product of V with respect to A. So that's basically corresponding to this right-hand side here. And again, because the index j is specifying uniquely how the product is coming about, we can simply exchange A and V because the order of the symbols doesn't matter. Note that since Aj is the transpose of Aij, we can write Aj simply as Aij transpose, and then we have something that corresponds to this vector Ci, where we have the V appearing to the right, similar to our vector B in front. So what I said before is that the index notation means that the order of the objects themselves does not matter. So Aij Vj is the same as Vj Aij because the operation, in this case the vector product, is uniquely specified by the index that's appearing twice. However, also what I said is the order of the indices are important. So in particular, Aij Vj is not the same as Aj Vj because Aj is the transpose of Aij, because the indices are entered in a different way. And if A is not a symmetric matrix, the transpose of the matrix and the matrix itself is not the same. So it's clear that these two represent different objects. However, we can interpret sort of sum over an index as a matrix product if the index that's summed over appears in the two symbols next to each other. So in particular, Aij Vj literally is the same as the vector product A with the matrix A and the vector V in this order, because the J is sort of appearing in this particular fashion. It is not true that if we had the index appearing somewhere, that would give the same product. So in particular, a counterexample to this would be the combination Aij Vj, where you note that the index that's summed over is I, and the I is here appearing as the first index. So basically this object here is not the same as AV, not the same as this one up there, because we can again reorder the symbol, so we can put the Vi all the way to the left because it does not matter where we write it. And if we do this, then we write Aij Vj is the same as Vi Aij. Now the I is appearing in the vector V and the matrix A next to each other. And this just represents an ordinary vector product. So this is the same as V dot A. And again, because A is not necessarily a symmetric matrix, V dot A is not the same as A dot V, which just proves the point that these two are different objects. Let me now talk a little bit about the norm of vectors. So in ordinary Euclidean space, we can talk about the norm of a 3-vector as the absolute value of the vector x squared. So in particular, we would have x squared being just the sum of all the entries of the coordinates, x squared plus y squared plus z squared. In index notation, we can write this sum here simply as xi, because that's how the index I is summed over. And we can write this as a particular combination xi, xj, where we introduce a matrix delta ij into the fold. And the matrix that gives us back this particular combination, we just sum up over the indices, is just the Kronecker symbol. It's just a matrix, a unit matrix that has ones along the diagonal and 0 everywhere else. And it's straightforward to check that this particular product of the vector x and this particular Kronecker symbol just gives you back x squared plus y squared plus z squared, the norm squared of the vector in 3-dimensional Euclidean space. It turns out that we can view this particular Kronecker symbol as something that sounds very fancy, namely the metric tensor of Euclidean space. There is a formal definition of a metric tensor, which I don't really sort of find very useful. For the course that I teach, in practice, all you need to know at this point is that the metric tensor is how you calculate the dot product of vectors. And the example that I had before is that if you have the vector product of two vectors u and v, you can write it as ui vj in the index notation with a metric tensor, and the metric tensor of Euclidean 3 space is just this Kronecker symbol, the 3-dimensional unit matrix. Now, if we take this concept that the length of a vector is expressed through the metric tensor, we can write the length of the vector in Euclidean 3 space simply as xi, xj with a metric tensor gij. And we know that for Euclidean space, the metric tensor gij is just nothing else but the Kronecker symbol delta ij. The reason for introducing this fancy notation is that it basically will provide us a view of more complicated general relativity metric tensors, basically by analogy. But here, the object delta ij is, of course, something of an overkill because we know how to calculate the length of vector in Euclidean 3 space. Nevertheless, formally, it's perfectly fine to call this the metric tensor and do operations with it, basically as an exercise. Now, let us consider a particular transformation of the coordinates in 3-dimensional Euclidean space. So we have the length of our vector that we can write down in index notation in terms of this metric tensor gij. And now we transform the coordinates by doing a rotation. So we write our old coordinates xi in terms of new coordinates x prime j. And the transformation from one coordinate system to the other coordinate system is just a rotation matrix rij. In the rotated coordinate system, we then will get a length of a vector prime that is just given as x prime I, and that we can write down in terms of the metric tensor in the rotated coordinate system. That is not necessarily the same, so it's noted as g prime, and that is the length of the vector in the rotated coordinate system. We can use the transformation rule between the unrotated and the rotated coordinates to rewrite the length of our original vector in terms of the new coordinates. So remember that L squared is just xi, xj, gij, and that we can write in terms of the new coordinates x prime by replacing every occurrence of x through the transfer coordinates. So xi is written as rij x prime j, and similarly for aj. So in order to not to sort of get mixed up with the indices, I use M for the transform of the coordinate xi, and I use N for the index that's the transform of xj. So if we rewrite this expression, remember that it does not matter where we put our symbols. I'll put the x prime m all the way to the left and the x prime n all the way to the right. And the order of those symbols does not matter because the product is uniquely specified by the ordering of the indices. If we then have this particular expression, we can formally just call this object that's appearing in the middle as G prime Mn, because I and J are summed over. So the only indices that are left of this object in the middle are M and N. So that will correspond to some object G prime M and N. And then we have something that's a quadratic form in X prime, and that we can recognize as our transformed length of the vector squared in the rotated coordinate system. So long story short, if we read this together with the original with the original expression over there, we find that we have a transformed metric tensor G prime Mn, which is just given as this particular combination Rij, Rim, Gij, Rjn. Again, we can reorder the symbols because the products are uniquely specified by the ordering of the indices. So we pull the Gij all the way to the right. And we will use some homework example to show that this particular combination, the rotation matrix, or the rotated metric G prime, is equal to the original metric in Euclidean space that was just a canonical symbol. So what we find is that under rotations, the Euclidean metric is invariant under rotations, meaning it is the same in each coordinate frame. And if that's the case, if both of those, the original and the rotated metric, are equal to the same thing, that means that the expressions for the norm of the vectors are the same in the both coordinate systems. And that just means that the length of a third vector is invariant under rotations. Of course, this is something that we knew all along, but the calculation here basically just shows that formally we can get the same result. And now having this math sort of at our disposal will allow us to say more complicated things about more complicated coordinate transformations as we go on in the course. And that concludes the present lecture.